Swayam Prabha. Digital India. Educated India.
Class number 5. We have been discussing diode circuits. Let's recapitulate whatever we have covered so far in this chapter. In this chapter we are basically going through different diode applications. In the last class we have started diode application on DC power supply. We all know that DC power supply system is very much important, and we basically use DC power supply system that is in adapter, because constant DC supply is required for our laptop and other electronic gadgets, whereas our line supply is AC supply. Okay, and let's go to that particular slide where we talked about our so this is the DC power supply, typical DC power supply, different building blocks. You see there is a transformer. The AC input is here, which can be depending on the requirement, which can be downgraded. Okay, of course that depends on N1 and N2. So anyway, we will get input AC signal at the input of this power supply. Okay, the first building block is basically the rectifier. We have gone through different rectifier blocks. For example, we have gone through a half wave rectifier, we have gone through full wave rectifier, and we have gone through bridge rectifier, right? In case of half wave rectifier, you probably remember that we will get only one half of the AC signal. Okay, here that is in case of half wave, and other half will be missing. Okay, so we lost one half of the input signal, whereas in case of full wave rectifier we get both the halves. Okay, and also in case of bridge rectifier we will get both the halves. The only difference is in case of between bridge and full wave rectifier, here we need 2 diodes. Okay, whereas here we need 4 diodes. And also you see here in each hub, in case of bridge rectifier, in each hub the signal goes through 2 diodes, so there will be 2 VD on voltage drop. Okay, or loss of 2 VD on, whereas in this case in each hub the signal will go through 1 diode. Okay, so there is a loss of 1 VD on, right? This part we have discussed already. And also PIV requirement in case of bridge rectifier will be less, will be half than that of PIV requirement of the ordinary full wave rectifier, because in the reverse bias the reverse voltage will drop across 2 diodes in case of bridge rectifier, whereas in case of full wave rectifier the entire reverse voltage will drop across a single diode. So PIV requirement is less in case of bridge rectifier. And also in case of bridge rectifier you don't need the center type transformer, which is a requirement for full wave. Anyway, we have discussed these things already. Now the second block is a filter circuit block. Usually we use RC filter circuit. Okay, the reason we need filter circuit, because you see there is fluctuation of the signal. Even if we manage to convert this AC signal and we have only signal in the same half, not in opposite half, there is no signal after the rectifier, but still the voltage is varying, right? And we are looking to make a DC power supply. So we use a filter circuit so that at the output here, this variation is much less. So you see, this is the rectified output, and what we can do with a filter circuit, we charge the capacitor, okay, and then charge the capacitor and then discharge it, okay. So this is charging, and then it discharge through your resistor path, okay, then it's charge again, then through resistor path this discharge, and so on. So you see the variation after this filter circuit will be much less compared to what it is at the input of the filter circuit, okay. So this is your rectified output, whereas this is your filtered output. So filtered output variation is much less, but what we still need to know is how much is this variation, okay. So if this is Vm, that is the maximum, and this is the Vl, that is the V lowest, okay. So we can find out this variation in the output of the rectifier, output of the filter circuit, and that variation is known as ripple, okay, or ripple voltage. That is nothing but Vm minus VL, okay. And in the last class we have found an expression of this ripple voltage, and we know that if we increase R and C of this filter circuit, resistance and capacitance, then this ripple voltage is going to decrease. And also if the input frequency is much higher, then the ripple voltage is going to decrease even further, okay. So this part we have discussed in the last class, okay. This class we will start from this regulator block, okay. This is a very important block. The reason we need regulator because you see there is considerable amount of ripple, even if there is even if we use bridge or forward bridge or full wave rectifier, and also after that if we use filter, still then there is a considerable amount of variation, okay. So to reduce this variation, we are looking for DC signal, we need to use regulator circuit, okay. So this is the regulator block, and we'll discuss how this regulator circuit, we'll discuss the working principle of regulator circuit here, which will show that even if this variation we will get this output voltage here will be fixed, okay. So let's go to the regulator block. Yeah, this is what I tried to mention, that this is the expression for ripple voltage, and we showed in the last class that if we increase C or increase R, this ripple voltage variation will decrease, or ripple voltage amount will decrease, and also it will decrease if we increase the frequency of the input signal, okay. So this is let's talk about voltage regulation, okay. So this is a typical voltage regulator circuit where we have a Zener diode, okay, and a resistor RS and a load resistance RL, okay, and there is a source Vs. Now this source can be the output of filter circuit, okay. Just now we showed that filter block, right? It can be output of the filter circuit. Anyway, let's assume that there is a voltage source Vs, a resistance Rs, Zener diode Vz, and RL is the load. So this is basically the simplest scheme of voltage regulator, okay. The purpose of voltage regulation is we want to keep this voltage across load, okay, fixed, okay, even if there is variation in RL or even if there is variation in Vs, okay. in even if both these variation, we want to keep this load voltage fixed. Okay, that is why we use voltage regulation block. Okay, now this voltage regulation block contains this RS resistance. This resistance is required because to keep the current through Zener below below IZ max. Okay, so this is the current through Zener. Maximum current it can carry is IZM or IZ max. Okay, if you buy Zener diode from the market, you will see in the specification sheet they have mentioned the maximum current handling capacity of the Zener in the when it is in reverse bias. Beyond that point, if you use more current, then the Zener will burn out. Okay, so what this RS will do, RS will restrict the current so that it will not go more than IZM referred in the specification sheet of Zener diode. Okay, so when I am using voltage regulator, we have to make sure this Zener is within this breakdown region. Okay, Zener is within this breakdown region, and also we have to make sure that the maximum current, say this is IZM, so maximum so the current can flow through the Zener should be less than IZM. Okay, that we have to make sure. So two things, one is it should be in the breakdown region, and also the current through Zener should be less than the rated value. Okay, but the key point is in this breakdown region, although I have drawn like this, in reality so there is a slope, you see, and you can find out RZ associated with Zener. That RZ I am not considering at the moment, but you can, when you solve problem from books, you will see some of the problem mention the resistance associated with the Zener diode while it is in the breakdown region. But what I want to point out is in the breakdown region, this slope is very steep. In other words, we consider usually VZ is constant, okay, once the breakdown occurs. But the important point is current can vary through Zener. Okay, in the breakdown region, current can vary. We have to make sure that current is below this IZM, so this so the key is voltage across Zener remains constant even if there is change in current through it. Okay, so that's the main important point when we are using this Zener as a voltage regulator. Okay, now let's discuss this in more detail. There can be two cases, as I mentioned already. One is when fixed Vs and variable RL, okay, that load resistance is varying, and the other one is variable Vs and the load resistance is fixed. So there can be two cases, but we have to make sure in both these cases this VL we have to keep constant, because that's the ultimate motto or ultimate goal of this block. Okay, so let's start point number one, where we are assuming this input voltage is fixed, so Vs is fixed. Okay, whereas this RL is varying. Okay, we will see how this VL will remain fixed even if RL is varying. Okay, so what we are trying to do now, we're trying to find out minimum and maximum value of RL. Okay, minimum and maximum value of RL. For that, this Zener diode remains in the breakdown region. Okay, if the Zener diode remains in the breakdown region, as I have drawn before, okay, this is the forward bias and this is the reverse bias. Okay, and this is the forward bias portion. We should operate in this region, as I mentioned to you before. So we have to make sure that Zener diode remains in the breakdown region. Okay, that is the key, because if Zener diode remains in the breakdown region, voltage across Zener will be VZ, that is fixed, because in the breakdown region we are assuming that this slope is very steep and voltage across Zener is not changing, only the current can change. Okay, so this if Vz is fixed, then VL will remain fixed because RL is in parallel with this Zener diode. Okay, so that's the key, that the Zener diode will remain in the breakdown region even if there is change in RL. Okay, now this RL, so we have to find out RL mean and RL max. Okay, for both these values, we need to find this range. In that range, the Zener should be in the breakdown region. Okay, so let's assume that let's find out RL mean. Okay, how we will find out RL mean? RL mean means that this load resistance is minimum. That means maximum current is flowing through load resistance, right? So if maximum current is flowing through load resistance, we can assume that the current through this Zener will be minimum. Okay, IZ is minimum because the maximum current is passing through load, so IZ is minimum. So we can assume that the Zener is just verge of breakdown. Okay, and when Zener is verge of breakdown, this current is basically very low current, that is the reverse saturation current, you remember, and that reverse saturation current is very low, usually nanoamp or picoamp, depends on many things, but we have discussed that before. So this current is very low, and then we can assume that this whole I1, that is the main current, is going through this RL, and very little amount of current through Zener. Okay, because we are finding out an expression for RL mean, so the maximum current is flowing through the load, and we are assuming minimum current is flowing through Zener, or what we are assuming that it is verge of breakdown. Okay, so only reverse saturation current is passing through Zener. So we can so that is how we can write VL over RL, that is the current through load. Okay, is equal to Vs over RL plus Rs. Okay, so that is the main current, that is basically your I1. Okay, that's this I1 we can write, and I1 we can write, and VL over RL is equal to Vs over RL plus RL. So from here we can write this expression, the value of VL. Okay, and we can write RL mean, because that's the RL mean, because we are assuming Zener is on the verge of breakdown. So RL mean is this. Okay, so we have to make sure that Zener is in breakdown, so we have to use RL more than RL mean. Okay, so what about RL max, because we need to find a range of load resistance within which Zener will remain in the breakdown region, and that will ensure that the voltage across RL is constant even if RL is varying. Okay, so how I will find the expression for RL max? You see, I1 is basically constant. Okay, I1 is the main current, that is basically constant. We can write I1 equal to Vs minus Vz over Rs. Vs is the main voltage source and Vz is the voltage across Zener. So I1 is the difference of these two voltage over Rs is basically I1, and here all these terms are in a constant term, so I1 is basically constant. Okay, and we can write IZ max. Okay, IZ max equal to I1 minus IL max, IL mean. Okay, because you see for RL max, that is the maximum resistance at here. Let me grab this. Let me erase all this. Yeah. Okay. So this is constant I1, and we have to find out IZ max, because you see we are looking for RL max. When it is RL max, the current through here is minimum because this is maximum. Okay, that means much more larger current is going through Zener, This is just the opposite case when we are finding out RL mean. So if current passing through Zener is more, we can say that we have to make sure this larger current is less than IZ max. Okay, we have to make sure that which is specified in the specification sheet of Zener. So IZ max we can write I1 minus IL mean, right? Because the IL mean is associated with RL max. Okay, so we know I1 because we know all these values. Okay, we know I1 and we know IZ max from the specification sheet, and from there we can find IL mean. Okay, and if we know IL mean, from there we can find out IL max, RL max, because IL mean is known from that equation and VZ is known to us. Okay, so that is RL max, and we can find out this way RL max and RL mean, and we have to, this circuit will act as a voltage regulator circuit if we manage to keep this resistance within this range. Okay. What about the second option, that is variable voltage and variable voltage source and load resistance RL is fixed. Okay, here load resistance, we are assuming load resistance RL is fixed, whereas source voltage is varying. Okay, like the one we have in the filter output. Okay, now if that is the case, we can find out again Vs mean and Vs max, like we did in the last slide. We found out RL mean and RL max. We can find out Vs mean and Vs max. How we can find out Vs mean and Vs max? Let's see that in case of Vs mean. Okay, in case of Vs mean, the Zener is, we are again assume like in the last slide, the Zener is just starting on the verge of breakdown here, because the voltage is less, Vs mean, so the voltage across Zener is also less. Okay, so so the maximum current is flowing through RL, you see, because this voltage is the current through Zener is very tiny. Okay, so the maximum current is flowing through RL. Okay, because it is just on the verge of breakdown. If that is the case, we can if that is the case, then we can say that we can write VL over RL, like in the last slide, VL over RL equal to Vs over Rs plus RL. Okay, and from there we can find out Vs mean, because we are assuming most of the current is passing through load. Okay, now this Vs mean is Vs mean is found out this way, and we have to make sure Vs is more than Vs mean, because that is the condition when Zener is on the verge of reverse breakdown, right? So we have to use Vs more than Vs mean. Okay, so that the VL and VZ will be equal to VZ. Okay, what about Vs max? Vx max can be found out in the same manner like we did in the last slide. Here IL is constant. Okay, and IL can be found out VZ over RL, because VZ is constant and RL is constant, because in this case RL is not varying, so we can say that IL is constant. If IL is constant, then we can write IZ max, because Vs max means the maximum current is flowing through Zener. Okay, and we have to make sure that maximum current should be less than IZ max. Okay, so IZ max that is defined in the specification sheet can be written as I1 max minus IL. IL is known from this expression. Okay, and we can find out I1 max. We can find out I1 max from here, because this you know from the specification sheet. Okay, the specification sheet you know of Zener. So you can find out I1 max, and I1 max can be written as Vs max minus Vz. So this this minus Vz by Rs, that is Is max, I1 max. Okay, and you can find out Vs max then, okay, from this expression, because I1 max is known to you from this expression, right? So you see, this way we can have the range of Vs mean and Vs max, and we if this regulator circuit will work properly, if the input voltage regulation is within this range of Vs max and Vs mean. Okay, now this is in a nutshell is in our voltage regulator. So the goal is we have to keep the voltage across load fixed, even if the source voltage is varying or the load resistance is varying. Okay, now there are two figure of matters which I just want to mention briefly. One is source regulation and one is load regulation. Now what is source regulation? Both these is usually represented in the percentage form. So in case of source regulation, this is a measure of change in output voltage, that is change in output voltage with a change in the source voltage. Okay, so del VL over del VS multiplied by 100. So that basically your source regulation. Okay, what about load regulation? Load regulation is the way we define load regulation. This is basically VL no load minus VL full load over VL full load and multiplied by 100, because it is represented in percentage. Both this regulation is represented in percentage. Now this VL no load represents output voltage for zero load current. So say this is my load resistance RL. Okay, so in case of VL no load, what we are doing, we are open circuiting this load. So whatever voltage we are getting is basically when we open circuit the load, whatever voltage we are getting at the output is known as VL no load. Okay, what about VL full load? VL full load is basically when the load resistance is minimum. Okay, whatever when the load resistance is minimum, so that is basically then maximum current is flowing through the load, and this voltage across this load we can measure is known as VL full load. Okay, so VL full load is output voltage for maximum rated output current, that is the when the load resistance is minimum, and here when the current is output current is zero, load current is zero, what is the voltage is, that is basically VL no load. So this is the definition of load regulation. So I encourage you to practice problems from the book using where they mentioned or asked about this figure of merits, this source regulation and load regulation, and also practice problems based on general regulations. Okay, that is the input voltage range or output load resistance variation range, and they will ask you to calculate, and also from do problems on rectifier and filter circuit. Okay, now apart from this we will discuss in next half an hour, we will discuss other two applications of the diode. One is limiter circuit and another is clamper circuit. What is limiter circuit? Limiter circuit or clipper circuit, also known as the name suggests, is basically an ability to clip off a portion of the input signal, ability to clip off or remove a portion of the input signal, but it the rest of the part of the input signal can go out of the circuit without any distortion. Okay, so ability of to clip off a portion of the input signal without distorting the remaining part of the alternating waveform, that's basically your limiter circuit or clipper circuit. Okay, so what we are going to do now is a very important application, because in many applications we might need a certain part of the input signal. So with this limiter or clipper circuit, we can remove the part which we don't need. Okay, so we will go through some of the examples of limiter or clipper circuit. Let's start with example number 1. This is a very simple limiter circuit. This example we have seen before or discussed before in our diode circuit, I think fast diode circuit class. Here we have an input signal, inputs AC signal, okay, sinusoidal signal, a resistance R1 and a diode D1. We are assuming that this diode is ideal diode, so we are not bothered about considering the V gamma or VD on. Okay, so if that is the case, then when during the positive half that diode is on, okay, and the diode will be basically diode is shorted or act as a short circuit. So if you measure voltage here across the diode, you will get 0 volt. Okay, what about negative half? Negative half of the cycle here, here basically diode is off. Okay, and here basically diode is on, right? When diode is on, the output measured across the diode is shorted, so no voltage you will get or 0 voltage you will get at the, whereas here you will get the entire input signal at the output. Okay, entire input signal at the, again in the positive half you will get 0 volt, and in the negative half entire input signal. Okay, so that way we clipped the positive half of the cycle, where the negative half of the cycle will come at the output. So this is a clipper circuit or a limiter circuit. We can add a voltage source here. Say in this example I have used a 1 volt source. Okay, in that case this diode will be forward bias only when the voltage here is more than 1 volt. Okay, you see, so in that case diode will be forward bias and diode will act as a short. Okay, and when it acts as a short, if you measure voltage at the output here, then we will get 1 volt. Okay, so that is here we will get 1 volt, because here the diode is basically on. Beyond that point, beyond this point, so here diode is basically on. Okay, so you of this part of the input signal, diode is basically on, and you will get 1 volt at the output, whereas in the rest of the, so this part diode is basically on, where the rest of the part diode is off, and when diode is off, entire input voltage will be at the output. So you will get at the output the signal like this. So you see the signal is clipped off where the particular part of the input signal where when the diode is basically on. Okay, now instead of 1 volt, if we apply more voltages, for example, if we assume that this DC voltage VB is much more than that of the peak voltage of the input signal, then what will happen? The entire the diode will remain off all the part of the input signal. Okay, so the entire input signal will be at the output. Okay, the entire input signal will be at the output. So V out equal to V in for the entire part of the input signal. Okay, so these are the 3 examples, and we will also discuss 2 more examples in the next page, on the next slide, but I would like to point out that these examples I have considered that diode is ideal. You should practice examples with diode VD equal VD on, okay, or V gamma, and also there are many permutation combinations possible here. You can reverse the diode polarity, you can add battery, you can reverse the battery polarity, etc., and so on. Okay, so let's discuss 2 more examples of the limiter circuit. In example number, in these 2 examples I have assumed that diode has VD on or V gamma across when it is on. Okay, so if that is the case, here you see that I have reversed the polarity of the diode. Okay, compared to the that what is there 1. Okay, so if you do that, you see diode is off all the time. Okay, diode is off all the time, and so if this is my input signal, if this, yeah, so if So this is my input signal, okay, V in. Now the diode will be on in the negative half, okay, and if I consider this is so this part diode will remain, diode will be on, okay, but rest of the part diode will be off. So say this is your VD on, okay. So you see you need so when this diode is on, when this diode is on and current flow through the diode, we will have voltage drop here, that is basically VD on, okay. Look at the polarity, so you will get minus VD on here, minus VD on, right, because this is your 0 volt, so it is minus VD on. And so you at the output you will get this entire input signal up to this, okay, because this part the diode is off, okay, only diode is on in this hashed portion of the input signal. I hope this is understandable. Let's discuss example number 5, where we have two diodes, diode and diode D2. We are assuming here both the diode has this VD on at the VD on as the when the diode is on, and there are two DC voltages, VB1 and VB2. Now you see if I apply an input signal V in, then if I apply an input signal V in, then what will happen? Then this one is just a second. Need two diodes D1 and D2, okay. We are applying two diodes here, as I mentioned. So and two supply voltages VB1 and VB2. So diode D1 will be on, okay, diode D1 will be on when this voltage here is if you see carefully, when this V in is at least VD on plus VB1, then this diode will be on, okay, right. In the same fashion, this diode D2 will be so this is D1, diode D1 will be on, and the diode D2 will be on, okay, when this when we manage to compensate this voltage VB2, okay, and this D2 will be on, okay. So this D2 will be on when here, whereas D1 will be on here. So D1 VD on plus VB1, whereas this will be on when this input voltage is minus VD on, current is flowing through this, and this is minus VB2, okay. So this will be at the output voltage if you measure at the output, okay. So you see the here D1 is on and here D2 is on, okay, but this part both the diodes are off, okay, this part both the diodes are off. So so the input signal is coming to the output, okay. So when both the diodes are off, input signal will coming to the output. When one of the diode is on, depending on which diode it is, you will get at the output that diode VD on and corresponding supply voltage. In case of D1 you will get V1 VB1, in case of D2 you will get VB2 along with the VD on, okay. I hope again this is understandable to you. Now let's discuss the last application, which is basically the clamper application, okay. In case of clamper application, what is the purpose of the clamping circuit? Clamping circuit basically shifts the entire signal by a DC level, okay. Say I have a input signal like this, okay, where the input signal is varying across 0 volt, okay, but if I use a clamper, we can move this input signal to a different voltage. Okay, say this is VDC. Okay, depending on my requirement. Okay, but this entire input signal will remain the same. Entire input signal will remain the same, so it will be the exact replica of the input waveform. Okay, but the output will be shifted by a DC level, DC value, right? That is important. And the how we can realize this kind of circuit? We can realize this circuit by using a capacitor and a diode. Okay, so capacitor is the heart of the component, so we need a capacitor and a diode. Of course, you can use additional resistors and additional DC supply depending on your the requirement. Okay, now let's discuss a couple of examples of the clamper circuit. One of the simplest example is the one in example 1. In this example, what we are showing, I have a capacitor C1 and a diode D1. Okay, and this is our sinusoidal input signal with a peak amplitude Vm. Okay, peak amplitude Vm. A sinusoidal input signal is varying, and so this will act as a clamper circuit. How it will act as a clamper circuit? Let me discuss the operation of the circuit. So when let's assume diode is ideal diode. So when diode is forward bias, the current will flow like this. Okay, and what it will do, it will charge this capacitor. So you will have the capacitor will be charged with the maximum or peak voltage Vm. Okay, and the polarity will be like this, because the current is look at the direction of the current, so polarity capacitor voltage will be like this. Okay, so once from this point, when the input signal is going down, you see the diode will be reverse bias, because then if I draw, so this is my Vm. So if this is beyond this peak value, this input signal, okay, then this diode will be reverse bias, because Vm is the maximum peak signal, peak amplitude, right? So this diode will be reverse bias, right? Now, if this diode is reverse bias, then what will, because you see the negative terminal is connected to P and positive terminal is connected to N, and also these voltages below Vm. These voltages below Vm in this part of the signal. Okay, so what will happen? So then this diode is open circuit. So we will have this, and the capacitor can't. So there is no current through this circuit. So capacitor can't discharge. So the capacitor voltage will remain the same. Okay, you see capacitor voltage will remain the same. If this diode is open circuit, you see this input voltage will be across the diode. Now, if you measure the voltage here, if you measure V out here, you will get this Vi, okay, plus this Vm, okay. But Vm polarity, look at the Vm polarity, it is opposite to the polarity of we are measuring V out, right? So what will happen? This AC signal, entire AC signal will be at the output, but it will be shifted by this minus Vm, okay, because of this polarity. So you see it is shifted here. So this is minus Vm, although this peak to peak value, that is 2 Vm, will remain the same. This is 2 Vm, right? As I mentioned that in clamp circuit, the whole purpose is shifting the input signal, but the entire input signal will remain the same. So input signal will remain the same at the output, but this its DC level will change. Okay, so as I said, V0 will be minus Vc plus Vi. Okay, and we will get minus Vm plus Vm sin omega t. So the entire input signal will be at the output, but there is a DC shift. Okay, the same thing we can discuss if we switch the diode polarity. So here you see, compared to example number 1, here we have reversed the diode polarity. Okay, and you see, if you think carefully, when the diode will be on, that is the negative half of the cycle, this negative part of the cycle here, the diode will be on. Okay, and it will charge the capacitor. So so it will charge the capacitor, so diode will remain on up to this point. Okay, and this capacitor will be charged, and this will become Vm. So this is your Vm or minus Vm, but here the polarity will be like this because the current is flowing this way. Okay, so if that is the case, again, like the example on the in the last slide. Okay, so if we measure the output voltage here, if the diode is open, you see the entire voltage, the entire input voltage will be at the output, and also a plus Vm shift. Okay, so if I draw the output voltage, we will get output voltage like this, where it is shifted by plus Vm. Okay, but this 2 Vm peak to peak value will remain the same. Okay, and the frequency remain the same, and so on. So you see, by changing the polarity of the diode, we can shift the entire AC signal to the negative side or the positive side. Okay, I have added an additional, with example number 1, we have added an additional voltage source VB. Okay, so if you add an additional voltage source VB, the entire output will be shifted. So this is your output signal. This blue color curve is the output signal. You see, it is exactly same as the input signal, but it is shifted, and that shift took you can think this way, that Vs equal to Vc plus Vb, right? Vc plus Vb is your Vs when this diode is on. Okay, and so this okay, and this will be charged, this will be charged up to Vm. Okay, so we can write this Vc is equal to Vm minus Vb. Okay, that is the maximum voltage this Vc can have. Sorry, that is the maximum the capacitor can have. Okay, now if that is the case, we can find out V0. Okay, that is the output voltage, that is Vs minus Vc, and we can replace Vc with Vm minus Vb. Okay, that is V minus Vm plus, sorry, minus Vm plus Vb. So you see in the this Vs is Vm sin omega t. Oops, sorry, and this is minus Vm plus Vb. If you see carefully, in the previous slide, this is minus Vm plus Vm sin omega t. Here also minus Vm plus Vm sin omega t, but additional Vb term is there. Okay, because of this additional plus Vb, this is get shifted. Okay, compared to what we have in the first example. So with this, we are basically completing our this class, in fact this chapter. So in this chapter we have discussed couple of things. We have discussed some simple example of the diode circuit. Then we have discussed rectifier. We have discussed a DC power supply. In that case, particularly we have used the application of diode as rectifier. We have gone through the application of Zener diode as a voltage regulator. Then we have gone through clamper circuit and limiter circuit. The purpose of limiter circuit is limit some part of the input signal, and the purpose of clamper circuit is clamp of the input signal to a particular DC value depending on the requirement. Okay, so with this we are basically finishing our chapter number 2. Okay, so that's the diode circuit chapter. In the next chapter we will go through BJT, that is an active device, bipolar junction transistor. So thank you very much. Bye for now.